Good evening and welcome everybody. This is Obi-Wan Pez for N Simplex Pachinko. We are doing some math tonight. Going to look at some of the papers that we were talking about in the past couple weeks. The Huygens and Galilei paper were just about 7 pages away from the end, and I'm guessing that a bunch of that is going to be acknowledgments and references. So, no, given that there's number 68 here, yeah, it's whew. Today marks our 4th affiliate anniversary, which probably means that January was our 5th streamiversary. And thank you everybody for coming in and hanging out for all this time, and showing me that this can be a fun activity and worth my time to come and try and educate people in terms of mathematics, in terms of the process, in terms of education, and just gives people a better sense of, you can do it too. I look a little washed out. Hang on one sec. I think maybe our lights got turned down. Yes. Yeah, it looks a bit better. Okay. So we did start a little bit late tonight, but I was waiting for my spouse to get home. I got a couple of other errands and things like that. I have had probably about 20 minutes to speak with her in the entire day. So, yay. She is currently working on a show in the Leeds area, so if anybody is up in Leeds, you might happen to see us at a theater in the greater Leeds area. And I had a good sit down for probably a good half hour or so before I came home this morning after coffee with the other Americans, and yeah, goodness, politics. Oy. So yeah, I was walking home and I was just like, you know what, this seems like a good spot to sit, and I just kind of sat on like a stone wall for a while and felt my feelings. Broke out the D&D notebook that I had been carrying with me, planning on doing some planning, and then flipped to the back page and started just sketching the building opposite me. It's not very good, and it's one of those that like I'm hopefully never going to show anybody because it's that bad. The sense of perspective is all off on the whole thing. I need to actually like get a draw in the vanishing point and all this stuff. But that's also not something I have to worry about. I can have my terrible drawings and I can feel my feelings and we'll have a good time. Righto. So in this section, Galileo Galilei and Christian Huygens 5, curves. I would like to discuss questions related to mathematical curves, in particular two geometrically defined ones, which have applications in art and science, and which attracted our attention, the attention of our two scientists, Galileo Galilei and Christian Huygens. The first curve goes by many names: catenary, hanging chain, and others. It is a curve on which both Galileo and Huygens worked, where the latter corrected the work of the former. The second is called the cycloid and is central to the theory of pendulum clocks. Both curves have also been used in architecture, the first in the construction of large domes and the second in that of bridges. We start again with the correspondence between Huygens and Mersenne. In a letter to Mersenne dated 28th October 1646, Christian Huygens raises another question that Galileo has already addressed, namely the form of the so-called catenary, i.e. the hanging chain from its two ends when it is subjected only to its own weight. In his Discorsi e dimostrazione matematiche intorno a due nuove scienze, published in 1638, a work considered one of the founding texts of modern physics, Galileo erroneously asserted that this curve is a piece of a parabola. In his letter to Mersenne, Huygens points out Galileo's error. He announces to his correspondent that he intends to send him, in a forthcoming letter, a demonstration of the fact that the curve is not an arc of a parabola. At the same time, Huygens writes that he will show Mersenne a calculation of the pressure that must be applied to a mathematical or gravity-free string to make it describe a parabola. Huygens also foresaw that this curve could not be described by a simple equation. It might be useful to recall here that mathematicians since antiquity have studied a large number of curves. The Greeks have extensively studied the conics, ellipse, parabola, hyperbola, but also curves known as mechanical curves to find solutions to some problems on geometric loci or some construction problems requiring mechanical instruments to be constructed. These include the Archimedean spiral, the cissoid, the quadratics, the conchoid, and many others. Because of their aesthetic appeal, all of these curves have been used in modern art. Right, so 68, the letter in Oeuvre Complète. In 67, catenary. Curve refers to in both Mersenne's and Huygens' letters as chaîne pendue or corde pendante, that is, hanging chain or handing rope, probably hanging. But there are other names: chaînette, ellipsoid, etc. Yeah, hang. Okay. Okay, so for this, Archimedean spiral. This is a curve used in squaring the circle in the trisection of an angle and in the 20th century in the design of gramophone records. They're very, very tight spirals, but nonetheless. Cissoid, a degree 3 curve used in the duplication of the cube, studied by Diocles in the 3rd to 2nd century BCE and by Christian Huygens and Pierre de Fermat in the 17th century. The cissoid, nope, that was the cissoid. The quadratics was introduced by Hippias around 420 BCE. It was used in the trisection of an angle. And conchoid, generic name for curves obtained as curves at a certain finite distance from other curves. The most famous conchoid is attributed to Nicomedes, 3rd century BCE, and used in the problem of trisection of an angle. Okay. The catenoid does not seem to have been considered in Greek antiquity. In the analytic geometry that has recently been founded at the time of Christian Huygens, the curves that were studied were essentially defined by equations, and the catenoid does not belong to this class. It was natural that this exceptional curve would attract Huygens' interest, given his curiosity and unconventional spirit. Huygens mentions his results on the catenoid at the end of a letter to Mersenne, 28th October 1646. I will finish for fear to detain you for too long, and I will send you in another letter the demonstration that the hanging rope or chain does not make a parabola, and what the pressure must be on a mathematical. That's a slight duplication. Hey, famished. Why, thank you. 4 years. Woo! Oh, the time? Yeah. The delay was just due to the messed up thing that we had going, because my my router is still acting up, but fortunately right now it seems to be okay. We'll see how long that lasts. It was doing okay earlier. We had some massive crashing with Elite Dangerous. I was doing more of the scientific survey. So, and then I thought, I could probably do this with, like, the real galaxy of all the stars that we know. But we'll see how that goes. Upgrade the route. We're leaving in a month. Or, yeah, in like a month. So, like, who cares? I have 0 energy to expend on this, given that, like, we're just going to be leaving. The guy can figure it out when he gets back. So we're under Virgin Media here, which was like our choice of provider. When we go to the new place, they already have BT, British Telecom, and like they already have a router. So, meh. Right. So, of which I found the demonstration not long ago. Right, from Oeuvre Complète again. Mersenne replied, Oeuvre Complète, 16 November the same year, stating that he was looking forward to reading Huygens' demonstration, that he claims it would indeed contradict what Galileo had believed. He added he would be delighted to understand, as the young Huygens thought he knew what pressure was needed to exert on the chain to make it form the parabola, and so what pressure needed to be exerted on the string to make it the shape of a hyperbola or ellipse. If you can do this, he writes, you will surpass yourself. Several epistolary exchanges took place between Mersenne and Huygens on this topic. The latter's letters contain mathematical propositions and demonstrations of the facts he claimed. The interested reader will find these letters in Volume 1 of Oeuvre Complète of Christian Huygens. Hey, Cy, how you doing? Yeah, the ISPs provide the router here. In theory, I could use it as a modem and then have a router of my own, like on the inside. Set it up as a separate firewall or what have you. But meh. This is, where are we? We're at the end of page 18. Galilei and Huygens, Music and Science. So Dr. Papadopoulos was looking at the history of Vincenzo Galilei and Constantine Huygens, who were the fathers of, respectively, Galileo Galilei and Christian Huygens. And both of the fathers were really into music. And so Dr. Papadopoulos was looking at, like, are these two guys were the scientists that we know also interested in music? The answer is yes. But, like, to what extent? How did it work? All that good stuff. I mean... Good temperature, maybe slightly oversteeped. Send your old Ray. I'm sure it would be terrible. You know what? I don't think it's oversteeped. I think it's just super concentrated because I put in less water this time, but I also put in less tea. So I missed that calculation, apparently. I wanted it to cool off fast enough that it wouldn't, I wouldn't be drinking it all night. Like I said, probably just not quite enough. Okay. To conclude this discussion on the hanging chain, let me mention that this curve in its inverted form was used in a number of dome constructions, including that of Santa Maria del Fiore Cathedral in Florence, the intermediate dome of the Pantheon in Paris, and the Chernobyl Arch, inaugurated in 2016, which covers the cracked former sarcophagus of the Chernobyl reactor. The reason is more than aesthetic. Spelled it right. The catenary is an arc whose weight ensures its stability. It plays a central role in the transmission of forces, yet another intuition of artists that has outstripped the formal proof of mathematicians. We continue now with another curve which attracted the attention of our two scientists, the cycloid. This curve is obtained as the trajectory of a point located on a circumference of a wheel as the wheel moves by rolling along a straight line. This curve satisfies a beautiful property known as tautochronism, which is to say that if we make a material point slide without friction along the curve, the point will always take the exact same amount of time to reach the bottom of the curve, regardless of what the initial height is. This is a fundamental discovery that Christian Huygens made while working with a pendulum clock. Blaise Pascal formulated several... He only made it to 39? Jeez. Several problems concerning the cycloid. Equation, arc length, area of region under the curve, volume of the body generated by its rotation, and so on. Such questions could not fail to interest Huygens, as they concerned a mechanically defined curve, a subject he was passionate about. Volume 2 of Œuvre complète contains notes by Pascal, extracts from his correspondence concerning this curve, as well as exchanges on the same subject with Pascal, Ismail Boléo, and other mathematicians. According to C. Devard, the editor of Marin Mersen's Correspondance, the problem of studying the cycloid was first proposed by Mersenne around 1615. Huygens discovered the tautochronism of the cycloid in 1658, realized that he could use it in his work on the pendulum clock. Indeed, he saw that if the pendulum was made to swing along such a curve, then the period of oscillation becomes independent of the pendulum length. With such a device, it is as if the length of the pendulum constantly changes, while the period of oscillation remains exactly the same. He discovered another important mathematical property of the cycloid, namely, if the pendulum is made to swing between two equal arcs of a cycloid, then its end, instead of describing a circular arc, describes a cycloidal arc. In mathematical terms, this means that the involute of a cycloid arc is also a cycloid. Galileo studied the cycloid before Huygens, and he liked this curve. He used it for drawing bridge arches. He did not foresee the properties that Huygens found. In a letter to Bonaventura Cavalieri, dated 24th February 1640, he writes regarding this curve, "It has been more than 50 years since it occurred to me to describe this arched curve, admiring its graceful curvature, to adapt it to the arches of a bridge. I have made several attempts to demonstrate some property of this curve and of the space enclosed between it and its chord, and at first I thought that this space could be 3 times the size of the circle that describes it. But that was not the case, although the difference is not great. On the work of Galileo Galilei on the cycloid, we refer the interested reader to Laloubert's edition. The cycloid as a curve had already been studied in antiquity and had attracted the interest of Renaissance mathematicians. Variations of it are extensively used in modern art." It remains for us to say a few words about Christian Huygens, the astronomer, as the heir of Galileo Galilei. Cornelis de Waert, un être édité de Roberval du 6 janvier 1637, contenant le premier énoncé de la cycloïde. Yep. Letter number 3972 of Galileo Galilei, Le Opère. 77 is the translation of this thing. Huygens to Cavalieri. So, yeah, the exact words to the translation that I read. Antoine de Lalouber, de cycloïde Galilei et Torricelli, proposition. Wait. Ah, crap. Yeah, that's Italian. De cycloide Galilei et Torricelli propositiones viginti autore la Lovera Societatis Jesu, or I suppose Latin. I don't know, man. Modern pieces of art entitled Cycloid. The number of pieces of modern art titled Cycloid is almost boundless. That might be going a bit far, but Galilei and Huygens. 6. Saturn. Huygens' main astronomical work is Systema Saturnium, a treatise published in 1659 in which he reports on his discovery of Saturn's moon and its ring. In 1657, he began observing Saturn with a telescope that was far more powerful than Galileo's. Magnification factor was 100, whereas Galileo's was only 30. Yep. I think mine could get up to 900. Oh, okay. No. We're good. Sorry, I noticed that the, like, Wi-Fi thing was active on my desktop, so that's really weird. That I don't like that. Okay. To Prince Leopoldo de' Medici. For Huygens, this dedication was another way of declaring himself in the line of Galileo, who had worked in Florence several decades earlier under the protection of the same princely family, and who, in January 1610, had discovered 4 satellites of Jupiter, which he had also dedicated to the Medici family, naming them Medicea Sidera, Medicean stars, in honor of Cosimo II, Grand Duke of Tuscany, and his 3 brothers, Francesco, Carlo, and Lorenzo. Galileo's discovery once again went against the Aristotelian belief that all the planets and other celestial objects revolve around the Earth, providing further indication that the Earth is not the absolute center of the astronomical system, and that the other planets may have their own satellites like the Earth has. Our 2 scientists, Galileo and Huygens, used telescopes that they had designed themselves. Huygens polished his own lenses. In fact, it was one of his favorite occupations. Galileo Galilei was able to observe Saturn's ring, but did not realize it was a ring. Okay. He considered it a mysterious object, called it mysterious appendages. In fact, depending on its orientation, the ring appeared in different shapes. Yeah, okay. It does tip ever so slightly as it's going around. I think it's like that. Precesses as it goes around the sun. So it will appear to be flat in some places and almost disappeared, and then in others it might be really close to 90 degrees on. So we can see all of it. It's not exactly there, but it gets close in some cases. No, it's not really. I think it only gets to like 30 or 45 degrees. But anyway, not the point. It was Huygens, with his powerful telescope and systematic observations, who realized that it was a ring, in fact, a collection of rings, and it is good to read an excerpt of the beautifully written description, a dedication addressed by Christian Huygens to Prince Leopoldo de' Medici. In this pamphlet, I study objects that are very far away in celestial space, objects that are outside the field of human observation, unless they benefit from the help of applied science. I am sure that many people will say that I have taken too much trouble to examine things which, according to general opinion, are of little concern to us, while there are still so many of those situated here below, close to us, that deserve to be studied. Oh my, that sounds familiar. But those who speak this way seem to notice too little how much the investigation of celestial things is superior to any other study, and how grandiose is the fact itself that our contemplation extends to parts of nature placed at such great distances, which, although appearing obscure and small, are nevertheless in reality brilliant and very large. For if we were to consider that these objects have little relevance to us because they are so far away, we would surely be unworthy of a mind endowed with the reason by which we easily ascend through the immensity of celestial spaces, unworthy also of that marvelous and never sufficiently praised instrument invented to extend vision, an instrument by means of which we also reach the region of stars with the sense of sight itself. It is by taking advantage of this invention that I have now penetrated further than anyone before into the remote domain of Saturn, Ao, and I have also reached so far that this immense road, only 100th part remains. If I had somehow been able to cross this last part, how many and what news, good gods, would I have to tell? Okay, 80. Systema Saturnium comes from Orbita Complete. The 4 satellites around Jupiter are known simply as Galilean satellites because it turned out Galileo figured it out before, discovered them before Huygens. Oh, no, no, no. Right, okay. Over time, right, Galileo called them Medicean stars, but over time people figured out, oh, wait, A, they're not stars, turns out they're moons. B, we're going to name them after the guy who discovered them. He was being humble / honoring his patrons. And 82. Huygens polishing his own lenses being his favorite occupation. This is another story, but it was through his lens polishing work that Huygens came into contact with Spinoza, who himself made his living from this activity. Talking about lenses, let me mention that Huygens was the inventor of the device known as the magic lantern, which used a series of lenses to project images painted on glass onto a screen or wall. Oh, simpler times. Finally, let me quote the beginning of Systema Saturnium, in which Huygens refers to Galileo's observations. When Galileo used optical glasses to contemplate the celestial bodies, and that, before anybody else, he had made known to mortals the remarkable planetary phenomena, the most astonishing of his observations seemed to me those he published concerning the planet Saturn. In the last section, I will consider a question of music theory to which I alluded above, namely that of temperament. Volume 20 of Christian Huygens' Œuvre complète is titled Musique et Mathématiques. Pages 1 to 174 of this volume are dedicated to music. It is not for mere coincidence that the editors of Œuvre complète have included both subjects in the same volume. Huygens' work on music is based on mathematics, in line with most of his eminent predecessors' works on the subject. In this respect, let me quote from a letter Huygens sent to R. Moray, dated 1st August 1661. I spent a few days studying music and the division of the monochord, to which I happily applied algebra. I also found that logarithms were of great use there, and from that point I began to consider these marvelous numbers and admire the industry and patience of those who gave them to us. Let me mention that Huygens' works on the theory of sound are not contained in the volume on Musique et Mathématiques. They are reproduced and commented on in other volumes of Œuvre complète, volume 19, whose general title is Mécanique théorique et physique. Okay. Theoretical and Physical Mechanics, which contains his notes on experiments of the human voice, on vibrating strings, the propagation of sound, and on other related topics. And volume 18, whose title is L'horloge à pendule ou à balancier de 1666 à 1695, in which part of his work on harmonic vibration is reproduced. Among the works included volume 20. Among the works included in volume 20 are essays on singing and others that contain valuable insight into the works of ancient and modern authors and the various modes, tetrachords, temperaments that they used. Two pieces are of particular interest here, each of which is a collection of notes devoted to temperament. These are La Division du Monocorde et Le Nouveau Cycle Harmonique. The former, written originally in Latin, is translated into French in Chapter 8 of the volume Écrits sur la musique, dedicated to Huygens' work on music, with notes and comments by the editors. This memoir consists of detailed computations based on the use of logarithms of a large number of temperaments and octave divisions. Some of these temperaments are divisions with quarter and seventh comma. I don't think I understand that. Huygens' main aim is to find a temperament that best approximates the accuracy of these intervals of fifths, fourths, thirds, and sixths. Systema Saturnium, text reproduced in Latin and French, volume 15 of Œuvre Complète. Robert Moray, 1608 to 1673, was a Scottish scientist and one of the founders of the Royal Society. And 85, that letter was part of Œuvre Complète. The second collection of pieces, Nouveau Cycle Harmonique, contains the foundations of Huygens' theory on the division of the octave into 31 equal intervals. Woo! Huygens recommends this temperament for both instrument and voice. He shows the differences between the intervals of this temperament and those of the mesotonic are indistinguishable. The pieces that make up this last essay contain highly detailed calculations of musical intervals. This work, which is probably Huygens' best-known contribution to music theory, had a non-negligible impact on the 20th century music. Bunch of stuff from Œuvre Complète. See footnote 42. Thanks. Mesotonic. Nope. Comments by the editors. Mesotonic or mean tone temperament is a temperament whose construction is based on the desire to have as many perfect thirds as possible. The impact of Huygens' work and the division of the octave into 31 equal intervals is discussed at some length in chapters 17 and 18 of Écrits sur la musique, which also covers some developments of the 31-degree temperament theory both before and after Huygens. Particular mention is made of instruments such as Niccolo Vicentino's arcisimbalo pentarmonico, Francesco Nighetti's cimbalo onicordo, as well as keyboard musical instruments built in the 20th century capable of producing Huygens' 31 sounds, reviewed by Adriaan Fokke, the Dutch physicist and composer who wrote music according to Huygens' temperament of 31 intervals. Fokke also discussed the relationship between Huygens' work on music and Leonhard Euler's work on the use of the harmonic seventh and the number 7, and his classification of genre. The same chapter includes an annotated description of several 20th and 21st century musical compositions based on the 31 sounds, works that demonstrate the direct impact of Christian Huygens' theoretical work on our modern music. 91. Right. I would like to mention the piece Notes se rapportant à des écrits de musicologues anciens. The full article in French translation can be found in Écrits sur la musique. In this article, Huygens provides a critical review of some of the musical works of ancient authors, such as Eratosthenes' Division of the Monochord, Marcus Maibaum's Tables, Theories of Aristoxenus, Euclid, Gaudentius, Ptolemy, Aristides, Quintilian, Wallace, and many others. He mentions Josefo Zarlino on several occasions in relation with his views on the ancients. I will focus on the latter, as Vincenzo Galilei was a vocal critic of his theories. In fact, I will quote Huygens on Zarlino's work from another piece which follows the one just mentioned, which is titled Notes se rapportant à des écrits sur la musique d'auteurs modernes. In this context, modern era is the one that begins with Francisco Salinas and Zarlino. The article is longer than the first and is presented in French of Écrits sur la musique. In this article, Huygens mentions the division between of the octave into 12 equal semitones in a paragraph that begins with Aristoxenus divided the octave into 12 equal semitones, which Vincenzo Galilei maintains is the best division. Mersenne uses it for the lute. In several places in this article, Huygens criticizes Zarlino's theories. In particular, he writes, Zarlino in Ragionamento 4, Proposition 1, says that the notion of temperament was discovered by someone else, without knowing who it was, and by chance. Similarly, in Book 4, Chapter 12 of Supplementi Musicali, he highly praises this invention. In the Instituzione Armonische, Book 2, Chapter 42, he describes the mediocre temperament in which major and minor thirds are equidistant from perfect pitch, and fifths and fourths are 2/7 of a comma apart. Again, not really understanding the whole comma thing. And in Chapter 43, he tries to show that there is no such thing as an acceptable temperament and disapproves of the one in which half comma is subtracted from the major tone and the same is added to the minor. The temperament is, however, true and excellent. At the time, however, this had not been fully yet understood. Indeed, Zarlino mentions that only the fifths and fourths remain just there. Huygens' criticism refers to certain passages in Zarlino's Dimostrazione Harmonische and others in Instituzione Harmonische. In particular, the last sentence of this passage refers to page 128 of Instituzione, where Zarlino alludes to a temperament in which the syntonic comma would be distributed between the major and minor tones, shortening one by half a comma and lengthening the other by another half comma, and in which all other intervals, and therefore fourths and fifths, are left in their natural proportion. However, in the true mesotonic temperament, the fifth is lowered by 1/4 of a comma, and the fourth raised by just as much. We have commented on all these criticisms in the volume Écrits sur la musique. A little further on, Huygens writes of Zarlino, he makes a big deal of what he knows of geometry, which only concerns proportions, as do all the others, like doctors in music, Boetius, Galerian, and Salinas, and again that Zarlino has muddled everything by mixing ancient music with it and its terms with modern, as in naming the tones by the names of the Greek hypaton, trite, diatsugemenon, etc., and always talks about tetrachords. This is followed by more technical criticisms of Zarlino's proposed interval arithmetic, in which Huygens points out the latter's errors. Huygens summarized in a synthetic way the 31-part equal temperament he recommends in his well-known Lettre à Bassogne de Beauval touchant les cycles harmoniques, known as Novus Cyclus Harmonicus, written in 1691. It's Don! How's it going, Don? Good to see you. Thank you very much. 4 years as affiliate, 5 and a little if streaming at all. This letter is accompanied by calculations and tables which show the difference between the intervals of this division and those of the fifth, corresponding to the proportion 3:2, the fourth 4:3, the major third 5:4, the minor third 6:5, and the major sixth 5:3, and the minor sixth 8:5. are so small that it is completely impossible for the most delicate ear to perceive them. In the same letter, Huygens notes that Silenus mentions this division of the octave into 31 equal parts, but only to condemn it. Similarly, he says Mersenne rejects it. In conclusion, he claims to have demonstrated the excellence of this division by the principles of geometry and to have upheld it against unfair judgment pronounced by the two famous writers. Let me conclude this chapter by a general thought on science. Yeah, thank you. Just got back from class, and Aaron's going to try to plow through some homework. Absolutely. That was one of my favorite things of coming out of, especially combinatorics class, because I was like, I can do this homework just like standing in line at Coldstone. It's great. 65 credits and trying to plow through the year. Woo! Which degree is this for? Associates in Science, nice. So you need like 60 something, 80 something. So in order to get an octave jump, I knew what you meant. So in order to get in order to get the next octave up on the same string, you can take the distance between the tight ends of the string and then halve them. So put a bridge back in at the half mark and then pluck, and it's gone up an octave. Take that bridge out, put it halfway again, pluck, that's another octave. So what we end up having is a right, distance is going to be equal to distance as a function of, no. Yeah. Distance away as a function of octaves, like the number of octaves that we're going. Right? It's going to take whatever initial distance it was, so d0, and then it's going to multiply it by a half. All right, minus 1, because for the 0th octave, no. The first octave mark should be placed at d0. So the initial distance, the first octave that we have. So we get a 1 for n. 1 minus 1 gets a 0 in the exponent. Half goes away. It's just left with d sub 0. Okay. So our first octave just gets us d sub 0. If we want the second octave, then this is going to get us d0 times a half. Third octave is going to be d0 times a fourth. Fourth octave is going to be d sub 0 times 1/8. Right, so it's just going to keep doing this. It is an exponential decay because we're trying to reduce the we keep needing to multiply our distance every time that we add a new octave. So going from one step to the next on both sides there. Right, the n is going to have an additive relationship from one place to the next, whereas the distance d is going to have a multiplicative relationship from one to the next to the next to the next. So this is an implicit relationship. Right, d sub, we don't even need to do that. D sub n is going to be equal to 1/2 times d sub n minus 1. Right, the new one is going to be just half of the previous one. So it's implicit because the relationship depends on the previous stuff that we were just talking about. Right, the previous number or numbers in the whole pattern. Whereas if we have an explicit relationship, the distance is going to be dependent only upon the position in the sequence or value of the independent variable. So, with Huygens insisting, or rather the other person, insisting that there needed to be 31 equal parts per octave, right? This ends up being really weird because if you want this to be split into 31 equal parts, what we're going to be doing here is we're going to say that now we want our n and d of n to look more like, here is 1. Now here is 1 and 1/31. Here is 1 and 2/31. Here is 1 and 3/31. As much as I hate using mixed numbers, it works pretty well in this particular case. So eventually this is going to get down to 1 and 30/31, and then it's going to go to 2. Right, 1 and 31/31. So now, right, this is adding 1/31. What is this going to multiply by in order to go from one step to the next? It just looks a bit bonkers there, doesn't it? Hey Rex, how's it going? Right, so what we see here is that in order to get from 1 to 2, we need to multiply by half. In order to get each of the individual steps that go from 1 to 2, the relationship is doing the same sort of thing, right? What we're doing is we're going to add 1/31 over on n, and now we're going to multiply by 1/2 raised to the 1/32 for all of these. Remembering that when we end up multiplying repeatedly over and over and over again by 1/2 raised to the 1/31, the exponents are going to add up together. So this means that every time we go from one note to the next in like on a piano and stuff like that, they're not using a nice like proportional mathematical formula to go from one thing to the next. They have to use irrational numbers. They're using the 31st root of 1/2 in order to get this particular thing. Now, in a standard piano, right, there are, goodness, how many keys? Well, 88 all the way, but no, don't do that. Virtual piano. Ooh, reject all. Right, save and exit. So going from 1C, yeah, going from 1C to the next, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 steps in a standard piano to get from one octave to the next. That's called the chromatic scale, to go from one octave to the next using our standard piano. We'll come back and talk about the calculations that were made and see how close we can actually get to getting the proper ratios for perfect seconds through sevenths or whatever. All right, see you in 3 minutes. Be right back. All right. Probably question the wisdom of eating all those cheese and crackers over there. All right. Dropping even 20. And 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 16, 17, 18, 20. Uh-oh. 2, 3, 4. Yeah. All right, 25 is good enough. Oy. Bashed up my knee pretty good this morning. It's not turning colors yet, so... Went to breakfast with a bunch of other Americans, and it's a thing we do pretty much every Monday. And I suddenly remembered that I hadn't canceled my other appointment to see some property or other, but we've already signed papers on the other one, so as a courtesy, right, let's cancel the appointment with the other people. So I called them back, and I had already canceled 2 others on the week before, but I was like, do I have any others in the database? Because I'd like to cancel those as well. So, of the 3, she found 2 of them and dropped them. And I didn't know if this other one was with a different agency or what. I couldn't remember. Kind of couldn't be bothered. So I called them this morning. I was like, oh no, I'm not coming to this thing. And they're like, oh yeah, we got that like so long ago. But as I was trying to get up and then get by all of the other people in the seats, I just ended up going bam, knee went right into this bench that was sitting right there, just at the right height, and just like hit that, just the very, very top of the tibia, the bone that's in the front for your shin, just the very top of it, right underneath the kneecap, just straight into it. So I made it outside, slightly limping and not swearing, before my leg went numb. I was like, that's not good. Alright, anyway. So with the standard piano, we've got 12 steps in the chromatic scale, which should be, again, evenly spaced from each other. However, you've got like full steps and half steps. And, the white keys are not always a full step part. That's really what the problem is. Right, so same deal. These are all multiplying by the 12th root of a half to get all their distances. But then to get like two notes that are exactly those are 1, 2, 3, 4. Oops. That's a minor. I'm not good at this stuff. Perfect interval. Here we go. Hey Phobos, how's it going? Good to see you again. Okay, so if we copy this image, bring it over here to here. Oh, no, it's not here. It's there. Okay, so two things that are in perfect unison are the same note. Perfect fourth, 1, 2, 3, is like, damn it. Okay, what do we have between a C and an F? So that's going to get us C sharp incidental, D sharp, E, and then it gets up to F. So that's going to be 1, 2, 3, 4. Okay, no, it's, oh man. It is actually 5 steps on a piano. So we're multiplying by a half raised to the, again, this is 1, 2, 3, 4, 5 twelfths. So the distance that we travel between those two notes is going to get 5 half steps going up the chromatic scale. So we get 5 twelfths of the scale, which then again, in terms of the length of the chord that we need, or the length of the string that we need, it's going to be 1/2 raised to the 5 twelfths of that distance. So then the perfect fifth, we've got, starting from F, we have F sharp, G sharp, A, B, oops, yep, A sharp, B flat, right. and C. So this is 1, 2, 3, 4, 5, 6, 7. Gross. 7/12. On the top end, that perfect fifth is going to be F sharp. F. Right, G sharp, A sharp, B, C. So from C to G, 1, 2, 3, 4 notes, but then it's 1, 2, 3, 4, 5, 6, 7. Right, it's still 7/12. And then the perfect fourth on the top is going to go from G up to C. So that's going to be 1, 2, 3, 4, 5 again. Yep. And again, perfect octave is going to be 12/12. So that's going to get you the string length of a half. And then again, times a half. To go from the bottom all the way to the top is going to get you multiplied by 1/4 the length of that particular string. Okay. Now again, the issue here is that when we look at like perfect fourths and fifths, these are now irrational numbers. But we just looked at this and said like, okay, the fifth is supposed to have a proportion of 3 to 2. Oops. So the question really becomes, is you know, a number, we're just looking at the ratio between stuff, is 1 over 1/2 to the 7/12 for the perfect fifth going to be approximately equal to 3/2. So 1 over parentheses 0.5 raised to the 7/12 is, yeah, right? It's pretty reasonable. It's actually 1.4983. So like, again, as it was said in the paper, most ears cannot possibly hear the difference between 1.5 and 1.4983 over, you know, that kind of distance there. And then what about perfect fourths? So 1 over 1/2 raised to the 5/12 approximately equal to, this is again, perfect fourth is 4 to 3. So 1.333 repeated. So we just do the same thing, but then change this number from 7 to 5, and we get, yeah, not too bad. 1.33489, and it goes from there. So these, at the very least, are not going to be obvious differences to our ears. It's going to be like somewhat reasonable. So this is one application of irrational numbers, where, like, if anybody's teaching students, they're like, when are we ever going to use irrational numbers in our life? You could just pull out a piano and be like, et voila. Anybody know why you pay $600 for a piano tuner to come in? Ours was about $200 to $300. All right, so I've also found an equivalent. 1 and 18/31 is going to correspond to 1.4955 on the ratio. And too far. Of course. 13. 1 and 13/31 is going to be 1.3373. So those are the ones we get. To correspond to our perfect fourth and perfect fifth. Okay. So again, we could get all of these, but we're not going to break it up. So this is the Salinas octave breaking into 31 equal parts. So in theory it could work, but then doing the chromatic scale going up, you'd barely be able to tell the difference between one note and the next. It'd be a little weird. Okay, in guise of a conclusion. We usually talk about the scientific revolution to designate the period of Western science around the end of the 16th century and the first decades of the 17th, roughly corresponding to the period when Galileo Galilei was most active. The term revolution in this formula is meant to suggest a break with the old and a radically new approach to the principles and processes of science, with a stress on experimentation. In this sense, in the word science, music is arguably included, at least for what concerns acoustics. Let me insist on the fact that even with a revolution taking place, the discoveries themselves remain very slow. They often involve the works of several generations of scientists. This is one of the conclusions that can be drawn from the account I have given here. acknowledgments, etc. 97, stress on experimentation. I would like to quote here Arkady Plotnitsky, who highlights the fact that the stress on mathematics is just as important, who prefers the term transformation to revolution, and from whom I borrow a statement by Heidegger. Modern science is experimental because of its mathematical project. For the source of Heidegger's quote, and also some reason for this view, see the article Arkady Plotnitsky, All the Resources of Pure Mathematics, Mathematical Physics and Mathematics as Physics in Essays on Topology. Cool. Well, we did it. Took us forever, but hey, it worked. ODEs. That's why I pulled this one. So we go with on the Picard-Lindelof argument and the Banach-Cacciopoli contraction mapping principle. The aim of this note is to present the simple observation that a slight refinement of the contraction mapping principle allows one to recover the precise convergence rate in the Picard-Lindelof theorem. Introduction. Ivan Grigorovich Petrovsky, in his 1939 textbook, gives the following 3 proofs of the existence and uniqueness of solutions for ordinary differential equations. Existence is proved by the Euler method of piecewise linear approximation of solutions. Existence of 2 distinct solutions with the same initial condition is then shown to contradict the Lipschitz condition. The unique solution is found by iteration of an integral operator. Existence and uniqueness are proved using Banach-Cacciopoli contraction mapping principle, to which I.G. Petrovsky himself gives the name Cacciopoli-Tikhonov theorem. In his first proof, Petrovsky uses a compactness argument based on Arzelà-Ascoli theorem, which therefore only yields the existence of solutions, does not give any approximation to solutions. Note, however, that the Euler method used in the proof of the Peano existence theorem can be shown to yield a sequence of piecewise linear approximations converging at a polynomial rate. So for this, what we're looking at is the Euler method is basically saying, okay, take your differential equation. The value of that differential equation at this particular location is the value of the slope of a particular line that you're going to use. So we're going to use a small line, i.e. line segment, and say from x0 to x1, we're going to draw a segment that has this particular differential equation valued slope. So, for example, this is the easy part. I can do this part. Right, if we got like y prime is equal to 7x squared minus 4x plus 1. Right, we're not going to get the middle term, so this is non-factorable, so whatever, it's fine. Okay, let's say that y at 0 is equal to -2. Okay, what we're going to do is we're going to take a delta x of 0.5, 0.1, and 0.01. When we do 0.5, we're going to get that when right, we got 0, 0.5, 1, 1.5, 2. All right, so the value of the differential equation at x equals 0 is going to be 1. The value where x equals 1, yes, I know. Value where x equals 1 is going to be 7 plus 1, which is 8 minus 4 is 4. And when it is 2, we're going to get 4 times 7 is 28, plus 1 is 29, minus 4 is 25. Okay, 1.5. We're going to get 7 times 2.25. I could just do this in the calculator. It's fine. Plus 1 minus 4 times that is going to be 6. This is going to be 15.75. Yep. Okay, so that's going to be 16.75 minus 6 is going to be 10.75. At 0.5, that is going to be squared is a quarter. So 7 fourths minus 2 plus 1. That's going to be minus 1. So that's going to be 3 fourths. All right, so we get the value y at 0 should get us negative 2. So when we plug in 0 for x, we do in fact get y equals b. So b has to be negative 2. Y equals negative 2. Therefore, y equals x minus 2 is going to be our equation from x equals 0 to x equals 0.5. Similarly, we're going to do the same thing with the next one. Y is going to be equal to 0.5x minus, then we have to figure out where the last one left off. So at x equals 0.5, that's going to get us 0.5 minus 2 is going to be negative 1.5. Where x is going from 0.5 up to 1 exclusive. All right, this one's going to be 4x. When x is 1, this is going to be at y equals negative 1. This one's going to be y equals 10.75x. At this point, it's going to be plus. Oh, that didn't work. Right, this needs to be plus b, where our 1 is going to get us the same value here and in here. So when we plug in 1, we get a -1 up there. When we plug in 1 here, we need to get a -1, so it's going to be b is going to be a -5. Right, this one's also going to be just b, I don't know what it is yet. X goes from bracket 1.5 to 2, open. All right, y equals 25x plus another b, where x is going from bracket 2 to 2.5. Same as all the rest. So this Euler approximation gets us something decent at least. All right, so 1.5, we plug it in here. 1.5 times 4 is 6. 6 minus 5 is 1. So at x equals 1.5, we need b it's less nice, but you know. Okay, so y equals 1 when x equals 1.5. Technically, this needs to be limits as we're approaching 1.5 because 1.5 can't be plugged into this equation. But we kind of arbitrarily cut it off at that point because we just can't have two functions with two different outputs. These have to have the same outputs for the endpoints. All right, straight down, 25. Here we do tens. Tens by fives, tens by ones, ones by tens. Seven times 5 is 35, plus 5 times 1 is 5, so that's 40, plus the 2 from down there is 42. To get the hundreds, we need to take hundreds by ones, ones by hundreds, and then tens by tens. Tens by tens is the only one that doesn't become 0. So that's going to be 7 plus 4 at the bottom is going to be 11. We already did that. These are all zeros over here. This is a 0 in the middle here. The only one that we're actually multiplying is going to be the 5 by the 1. Plus 1 is going to get us 6. That seems unlikely. Oh no, 16. Hang on. It's got to be. Yes, right, because the 1 times the 1 here is going to get us the next number up. So 16.125. We need y to be equal to 1. So it'd be 1 minus 16.125. So negative 15.125. All right, last one, and yeah, definitely a minus. Same deal here. When x is 2, we're going to get a 21.5. 21.5 minus 15.125. Which is a 6.375. So then we need this to be at 2. Y equals 50 minus to be equal to 6.375. That's 43.625. That's a problem. We need blue to intersect at this red one here. This is why I like point slope better. right? 0, 2 is going to be the individual point. So then we get y equals m x minus x1 plus y2. So y equals m. The slope that we had at that particular point was 1, so then it's going to be x minus need the point. So this is going to be where we get 0, negative 2. So y equals x minus 2. Then between them, we've got 0.5, comma, okay, so this is y equals 0.5 x minus x1 2, I guess, plus what? Oh, right, that's supposed to be in y1 there. Consistency's sake and all that good stuff. So do be careful. Y equals 0.5 times the quantity. This is x minus okay, so if it is a half, right, that is x equals a half plus hmm. At least I know it worked. Okay. So this is going from 0 less than x less than 0.5. Zero 0.5 less than x less than 1. This is 1 less than x less than 1.5. Ooh. Right, because I altered the other one, so now it has to come down by a half as well. So this is going to be 4.5. Ooh, no, 5.5. Okay, 5.25. Negative 1.5. Yeah. Negative. Right, so then 1 by should be a positive 0.75. That was not what I was going for from earlier. -3. No. That's 5.25. What is going on there? Well, I did something wrong, clearly. X minus 2 point in there. That negative 1.5 is the y value that we got for that. Then do that. You could plug it back in. That's fine. Then all right. supposed to be a negative somehow? No. That'll be fair if we just do it like point slope form, right? This is going to be, our x is going to be at 1.5. And then our y is going to be at plus 0.75. And then we're only doing this from 1.5 less than xx less than 2. Right, then we could just multiply all this stuff out too. Get the point slope, or get the slope intercept form. Okay. So this is what the Euler approximation for the solution to this particular differential equation would be, given that the initial condition y of 0 is going to be equal to -2 with a delta x of 0.5. We could repeat this with 0.1 and 0.01. Obviously, that's going to take 5 times more and then 10 times more calculations to actually do the same amounts. However, the basic idea is going to be the same here, is that we're going to get a much more gradated curve here for each of these bits. So we get a more and more curved approximation for that. That's going to look really good. Or, yeah, a curved approximation of the actual solution. The actual solution to this differential equation is not particularly difficult because it is separable. It is already separated. The y prime is dy dx, and so we kick the dx over to the other side. We're left with dy on the left, and then integrate both. And it's going to be a pretty simple cubic equation on the right that we end up with. So oftentimes we do want to attempt differential equations using like Euler's method or Runge-Kutta or whatever. Try a couple that you know what the original function should look like, and then once you figure that out, then start pulling some weird ones. Perhaps even some differential equations that like you can't solve. So something like, y prime is equal to natural log x over x squared minus x times natural log x minus x to the x over, I don't know. Over x factorial. Nah, maybe that's too much, but it is well defined, but that's not really the point. Over, nah. Sine of x times the, I don't know, some other function. E to the negative x. Right, something like this. It is separable. You could, in theory, do it, but the issue is going to be like, do I know how to do a natural log with all these bits? And that's actually doable still, because we could do integration by parts on most of this. But if we went with something like that, I'm not sure you'd be able to work it out. What's another function we could use that's not polynomial, that's not... It's not like it really matters, but... So, anyway, once you get a differential equation that's got a bunch of terms in it, it looks really ugly. We could end up looking at this and be like, all right, well, I can't actually solve it as is. However, obvious. There you go. Throw in a y there as well. If the derivative depends on y in any way, shape, or form, we're not going to be able to separate this. Well, okay. In this one, we're not able to separate because that single term, natural log of x over x squared, doesn't have a y squared as well. We're not able to clear it out by multiplying by y squared. Good evening, Slim. And good evening, everybody from Academy of Useless Ideas. My name is Obi-Wan Pez. This is N Simplex Pachinko, and we were just about to wrap things up here and pass things off as well. So sorry, everybody. Either that or go straight into an ab break, which I know is also terrible. Thank you so much for the affiliate anniversary wishes. Everything's been going pretty well up here. So, hey, our internet didn't crap out, so that's pretty awesome. So, let's see. Just while we're finishing up here, yeah, let's go see paleontologizing. Dr. Danny Anduza will jump out before the ads hit. So, we were working on all sorts of stuff tonight. We were talking about some math communication. This one was on the Picard-Lindelof argument and Banach-Cacciopoli contraction mapping principle, which has to do with the existence and uniqueness of solutions within differential equations. So I had gone through some of this stuff and said, okay, let's try and figure out like what this is saying. So it was saying that the Euler method in use here, which we were just showing on the other screen, is able to yield the sequence of piecewise linear approximations converging at a polynomial rate. So if we were to start with this one, which gives us a half distance between each of the things, and then expand it out further, and then get a smaller and smaller and smaller delta x, then it does really awesome stuff. That, again, starts approximating better and better at a polynomial rate. So it's pretty cool. We're going to go over and see Dr. Denny Enduza doing paleontologizing. I hope you all have a good night. My name is Obi-Wan Pez. This is N Simplex Pachinko. See you later.